equation. So we did this one using a graph. We invested $1,500 and it accumulates to a value of $37.50 at a rate of 8%. That's okay, Brianna. Compounded monthly. Remember doing these? Yeah, this was probably like a month ago. And this is in your notes. We did this problem. So if you look back, and maybe look back, so you see where you did your applications. Way in the beginning. It was after transformations. It was on one of those packets. It was on the second packet. It was on the second packet in number 3. Okay, so we set this up. We put this here. We had this. We did this, the rate. I needed quiet, guys. And we didn't know how much time that would take. Now, if you remember, we did this graphically. We did an exponential curve in quadrant 1, and we did an intercept. Remember, because we weren't sure how to solve this algebraically, because we didn't address the logs yet. So now that we know how to do logs, we know how to bring down your exponents. Now, if it's possible, we just trace this. Oh, it is today's list is over here. Now, if it's possible, you have like 2 ways to do this. If it's possible to divide it out, you can divide it. If it's not possible, we'll do it the long way. God bless you. So if we were able to divide 1,500 into 37.50 and it went in nicely, we would divide it out. That's like your double, your 2 to 1, your whatnot. But since it doesn't divide in nicely, just grab one of those sheets, please. The only way to get your exponent down is with a log. This exponent only belongs to this factor. So when we take the log of both sides, or the ln, it doesn't matter. Work with me on this, guys. It's on your sheet. We still can't bring down that exponent until that factor is isolated by itself. Now, this is your product. The log product rule says turn this into what? When you were multiplying like bases, what did you do to the exponents? Add them. So we're going to turn this product into an add. Then we can bring down the exponent. This thing looks a little messy, but that resolves by itself because there's no variables in that part. Now our goal is just to solve for our variable. And here's your variable right here. So we have to isolate that term. So we're going to subtract this log from both sides. And remember, we don't subtract the numbers. We have to physically say the log of 37.50 minus the log of 1,500 equals this little mess over here. Now, if you really hate to have all these parentheses and all these extra things in here, if you resolve this part right here, because we round to 3 decimal places, if you're going to do any interim rounding, round like 5 decimal places, because you don't want to throw off the rounding at the end. Technically, we shouldn't round till the very end. But if that bothers you, put it in your calc and round it to like 5 decimals. Just go a few more than the 3. And it'll catch your rounding at the end that way. Now, we want to take and solve for take. Just grab one of these sheets. So we're going to divide this little mess by this. This looks a lot worse than it really is. Okay? One thing you're going to have to remember when you do this is parentheses here, parentheses here, if you don't have a fraction key. The numerator and your denominator must be in parentheses. And you can put it in just like that. You can do log or you can do ln. All we did was we needed to get this down. If you want to cheat a little bit, you can divide this out. And this doesn't divide very nicely, but it actually isn't too bad. If you divided this out over here, 1500, divide this out first, it comes out to 2.5. So this would look like this. And if you want to put this in your calculator, let's see how bad that looks. That comes out to a long string of numbers. So instead we can just do this. Just give me like a bunch of decimals. Does that look better to work with? Okay, if you prefer, this really is the right way to do it, the long way, because we have to round to 2.5. You can divide out because it terminates. It's not so bad. You can get rid of this, and you can keep that if you want to. But if you work that out, that's not so bad either. Now, when you take the log of both sides, let's take the ln of both sides, just to be different. You're going to bring down this. Okay, so now you're going to divide both sides by 12 ln. Okay, does that look a little bit better?
So where did you get 2.5 from?
I divided out 1500 into this.
So what'd you get when you divided 12 log 1 plus 1008?
All right, let me ask you, are you okay with this first? I'll erase this and start it again. Are you okay with this? This was a long way. It's the correct way. That's the long way. So here's the incorrect way.
What's still the answer to that?
It's still going to be the same answer.
So you 2.5?
No, well, I didn't even do the answer out yet. Let's backtrack into this. Are you all okay with this formula? We developed this formula before. We graphed it in L1, L2. Okay. We said this goes to this. So let's get rid of this factor. Let's divide both sides by 1500. This was not so bad because it reduced it down to 2.5. So then I said, okay, if that parentheses is bothering you, this guy, God bless, put it in your calculator, but because we round the final answer to 3 decimals, you have to go out a few more decimal places. So round this out to 5 decimals. This all comes to 1.00666. Okay? Good so far? I'm just getting rid of like the mess for you here. Now, you need to solve for your variable that the log rule will bring that down. So take the log or the ln of both sides and bring down your variable. You need to solve for t, so you're going to divide both sides by 12 log both sides. Order of operations says, though, you need to put this in parentheses if you don't have a fraction key. Because otherwise it will take this log divided by 12 and then multiply that answer by this. So whenever you do more than one thing in the numerator or the denominator, put parentheses around it. Either one will give you the same answer. And we got the same exact answer as we did when we graphed it. We have to. It's going to take 11.492 years. If you look this back up in your application packet, when we graphed this, we had an exponential curve, and we had the 3750 come across. And where they intersected was our answer. Yes, it was probably a lot easier than doing the log, but if you have to solve it algebraically, you have to use a log to bring down your exponent. This one's kind of messy because it's got a lot of things going on. You have your fractions, you have decimals, you have a lot of things going on here. Is this better than doing the whole thing out for you guys, one step at a time? Simplify it one step at a time before you take the log of both sides. The other way is the proper way to do it. Yeah, one step at a time. Do your product rule. That's why you know your rules. This is the little cheating way. Technically, if you could bring this piece, this 2.5 terminates, that's fine. If you could bring this piece all the way down, then you're still okay. You're still good for that. Okay? Makes sense? Kinda? Let's try another one. Okay, we did this in that same packet. This is when we were compounding your money. We said determine when an investment doubles if the in value at 6% compounded continuously. This was one of your problems. Compounded continuously is per. So we kind of took a shortcut. We said doubles. Anything that you put in and you double, and then we divide it out. And this is why we divide it out. If I invested $100, it's going to double to what? Now you all were okay when we did this, remember? This goes here. So we divide it out by 100. And we said 2 to 1. Remember doing this? Triple, 3 to 1. And this is how we did this. So we're going to break it down to 2 to 1. We're going to put your rate in. And I don't need the 1. So your rate is at 0.06. And we don't know your time. Now we need to, bring down that exponent. The only way to bring down a variable in your exponent is with the power log. So therefore, we need to apply logs to both sides. They have to be one term, one term. They can be more than one factor, but they have to be one term, one term. Now because this is your base E, we have to use your ln for this side. You don't get a choice in this one. You have to use the ln to both sides. But you have a very nice little property that says what happens to ln E? It cancels out. So we have ln 2 is equal to 0.06 t. Now what do we do? Divide both sides by 0.06. And you should get the same exact answer that we got before. It was going to take 11, and again, 3 decimal places. If you're dealing with money, if you're returning money, 2 decimal places. If you're returning time, anything else, 3 decimal places. Now, I'm going to run this side by side because I want to show you it's no different if we did this out the long way. I want you to be comfortable with this. If you see your E and you say, okay, I need to take the ln of both sides, say we didn't divide anything out, I need to get this down, but it only belongs to the E. So you have a rule when you do a product. We turn this into an add. This is what we worked on. Then you can separate this of the R. This is supposed to be 0.06. So the ln E comes out. And all you're going to do first is subtract this guy so we can isolate your T. See it? This This is using all your rules. This is making good use of all your rules. But we took a little shortcut. I knew when we doubled, we could go 2 to 1. The 1 we don't need to use. But if there is something else out there, and it's a product, use your product rule. This is why we learned all your rules. Questions? Are your brains frozen today? Okay. We'll try one more together, and then I'm going to let you do the rest. There's probably not a lot more. I'll do one more with you, the population of the town. Remember the population of the town increasing, decreasing? We did this also with your curves. We solved it graphically. The population of the town is decreasing, and we want to know when it will be 50,000. We started like this. We did this part already. We put in your y. When will it be 50,000? If it starts at 123 and it's decreasing at this rate, okay, I'm decreasing. Now, you again have a couple of choices. This is the product. If you decide to divide by 123,000 into this and get your one term set up a little bit nicer, let's see what happens there. I don't usually do it that way, but if that's the way you want to do it, it's quite a long decimal. Here's another way you can do this. Watch. Just reduce your fraction and leave it as a fraction. Are you okay with leaving this as a fraction? Can we subtract that guy? Will that make life easier? 1 minus. Does that look a little better? If you need to, you can string this out to go like 5 decimals. If you need to. It's a weird decimal. It's an irrational number. So you would have to go out at least this many decimals. But to avoid that, you can leave the fraction. When we do the log, you don't have to use the quotient rule for that. So we're going to take the log of both sides. That's the only thing that's going to bring this down. And if you want, you can take the ln of both sides. Bring down your t and divide both sides by the ln of 0.97625. Just be careful that you will, I think your ln gives you parentheses here, so you should be fine. You don't need any extras. When we did this before, we had a decreasing population. We wanted to know where the cutoff was at 50,000. We graphed it in your y1, your y2, and now we're solving it algebraically with your logs. So your answer will be exactly the same, 37.45 years. Now, I tried to write where each one came from. We had 2 parts. We did the first part was like this, and the second part was with the investments. So if you want to go back to your applications and pull out your equation, you don't have to rethink the equation. All you have to do is solve it algebraically using a log. So you already have all the equations for those in your notes, because we did them graphically. So now what all you're doing is solving them algebraically. Questions? Not getting happy faces out here. So you have 12 minutes before the end of the period. It's a good time to work on these.